A magnetic field can be represented by lines, just as we represented an electric field by lines. We draw the line so that the line through any point is tangent to the magnetic field vector at that point, and so that the lines per unit area perpendicular to the lines at a given point is proportional to the magnitude of the field at that point. We call these lines magnetic field lines. They are sometimes called magnetic lines of force, but this term is unfortunate because, unlike electric field lines, they do not point in the direction of the force on a charge. So I'm just going to read this. In a uniform magnetic field where the B vector, the magnetic field B vector, has the same magnitude and direction at every point in a region, the field lines are straight and parallel. If the poles of an electromagnet are large, flat and close together, the magnetic field in the region between them is very nearly uniform. Magnetic field lines produced by a few examples of magnetic field sources are shown below. So this is A, B and C. A bar-shaped permanent magnet. So that's got a north and a south pole, and these are the field lines. Notice that the field lines are very narrowly spaced here. The force of the field here is very strong because of these narrow bands. As we come out here, the strength is weaker because the field lines are further apart, and you can see the direction of the field lines is given by these arrows. So if we stick a monopole here, it would feel a force pushing it this way, and not there is such thing as a monopole. B, a coil of wire wound on a cylindrical form that is a solenoid. So here, look, we have a battery. The leads that go into a solenoid, which is a helical winding of wire, and that again causes a magnetic field, and you can see the field lines coming out very similar to the magnet. In there, they're almost uniform here, and as we get out here, they're not uniform. Look, they're diverging here and they're diverging over here, so that wouldn't be uniform. They're not uniform, they're bending over here. But in the middle here, when we want to do calculations, we like to work with uniform field. And then finally C, a laboratory electromagnet with an iron core. Here the magnetic field is nearly uniform in the gap in the core. So here we've got this, and you can see here that the field lines here are going round. This is a coil here to a battery, and it's causing these field lines. And you can see here between the poles here, you've got a uniform field. In all above three cases, the field lines are continuous curves closed in on themselves. There are no endpoints here. So unlike the electric fields, which has a positive and a minus charge, and you're seeing the field lines leaving the positive and terminating on the negative, with magnetic field lines, there's no start and end points. They turn around in on themselves. You can see each is a loop. So there's no start and end points. You know, this one here has come we don't show this one, but it's come all the way around and it's back in again. Every one of the lines is a completely closed loop. So that's the difference between magnetic field lines. Well, one of the differences between magnetic field lines and electric field lines. There are no sources or sinks, if you like. It's just one continuous loop.